Good day and welcome back to the second part of our discussion on vector fields. In the previous video, we introduced vector fields and we explored several examples and illustrations. In this video, what I'd like to do is to specifically concentrate in on what is known as a gradient vector field, which allows us to visit a familiar topic we've previously encountered and also lay the groundwork for a future topic. For a function of multiple variables, f of x, y, we define the gradient of f, as we did before, to be a vector in this case with two entries, partial of f with respect to x, and partial of f with respect to y. And recall, we can extend or generalize this definition to a vector with as many entries as we would like. In this case, we refer to it as the gradient vector field. And furthermore, I'm going to note as well, we call the function f a potential function. And a common problem for us in upcoming sections will be to identify when a vector field is a gradient vector field, and if it is, we'll want to be able to find that associated potential. So to begin, let's revisit an old example. Let's just find the gradient vector field, associate it to some function. So following our template from above, we know that the gradient vector field will be a vector with two entries. The first entry is the partial with respect to x, and the second entry is the partial with respect to y. To differentiate with respect to x or y, we use the chain rule. So we think we take the derivative of the outside, 1 over 2 square roots, evaluated at the inside, and then we multiply by the derivative of the inside. But when we differentiate the inside, it's with respect to x. So simply 2x. And then similarly with respect to y, 1 over 2 square roots, evaluated at x squared plus y squared, times that partial with respect to y. So we can cancel off the 2's and combine this to make it look a bit nicer. X over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared. And it turns out that we can use our previous knowledge and investigations into gradients to help us sketch gradient vector fields. And I have a small typo there, missing a square root. So for this function that we've just worked with, let's sketch several associated contours along with the gradient vector field determined at several points. So let's begin with the contours. So reminder from previous discussion, and in this case because it's a square root we would say a positive value of k, we could have the k equals contour. And in our case that k equals contour would be given by the curve x squared plus y squared equals k. And in this case, we can note that this k contour would be a circle of radius k, square root k, excuse me, centered at the origin. And if we wanted to sketch several of these contours, that would be a quick and easy task for us. The k equals 1 contour would be a circle of radius 1, centered at the origin, and the k equals 4 contour would be a circle of radius square root 4, or in this case 2, centered at the origin. And I am only sketching enough of these contours to get an idea of how things will look and how these gradient vectors will behave. And before attempting to sketch some gradient vectors, let's pause for a reminder that we've previously encountered. What we've seen is that the gradient of f at some point, x naught, y naught, is perpendicular to the contour at x naught, y naught. And furthermore, just for fun, if we wanted to know what is the length of a gradient vector, just to get an idea of how long should this vector I draw be. Well, looking above, we recall that the length of a vector is the square root of the sum of the components squared. So it would be x naught squared over x naught squared plus y naught squared from the square of the first component plus y naught squared over x naught squared plus y naught squared from the square of the second component. And if you add those two quantities up, it simply ends up being 1. And this should give us a very good idea as to how we should expect some of these gradient vectors to look like. They should be perpendicular to a contour, and they should have length 1. And if I pick just a few random examples, perpendicular to the contour, length 1. And remember, I'm not going to try to draw each and every one of these, just enough to give us a little bit of intuition related to this vector field. But once again, the key observation is that a gradient is perpendicular to a contour, a topic we previously encountered with directional derivatives. And it turns out that gradient vector fields are an important topic that we encounter frequently in upcoming sections, and for that reason we give them a special name. We will refer to a gradient vector field as being conservative. And a common question that we will need to answer, it will in fact be a smaller part of a larger question in future topics, will be, is a given vector field conservative? And if it is conservative, can you find that so-called potential function, little f? Now let's think about this intuitively. To ask if a vector field is conservative is a fancy way of asking, is there a function little f where the first component of this vector field is the partial with respect to x, and the second is the partial with respect to y. So essentially what we want to know is, can we find a function of two variables such that the partial with respect to x is the first entry in the vector field, and the partial with respect to y is the second entry in the vector field. And if such a function f exists, we could claim the vector field is conservative. But in order to find that function f, we need to undo these two partial derivatives. That is to say, from this first equation, we get a representation of f. It would be the antiderivative of y cosine x plus 2 with respect to x. Because if we are going to undo a partial with respect to x, we do so by anti-differentiating with respect to x. So treating y and 2 as a constant, we would get back y sine x plus 2x, and it is an indefinite integral, so we get back a constant. But this is a subtle part of the problem. We have to remind ourselves, what is the purpose of this constant? It should represent every quantity such that when we differentiate with respect to x, we end up getting back 0. But if we talk about differentiating with respect to just x and getting back 0, that could be a true constant, or it could be a constant with respect to x, which means it can involve y's. And how I typically represent this is just c sub y, indicating constants or quantities only involving y. And this is the reason why just working with the first partial is not going to be enough for us. We also need to consider f sub y to hopefully narrow down the choices for that constant involving y's. So we play the same game a second time. We note the partial with respect to y is sine, so that f should also be the antiderivative of sine with respect to y. That is, we treat sine x as a constant to get back y sine x plus a constant. But because this constant represents all quantities whose derivative with respect to y is 0, it can involve an x. And if f is truly conservative, we should be able to combine together so that we represent f as a single function of x and y. So comparing our two representations, the following rule of thumb should be considered. Any quantity involving both x's and y's, so think y sine x, y sine x, that should appear in both representations of f. we write that down. And then anything left over should only involve a single variable. Note the constant with respect to x can be 2x. And the constant with respect to y, well, we're not seeing anything, at least explicitly here, with the second formula. So one thing we could do is just go ahead and let it be 0. It doesn't actually have to be any physical quantity. And for this function little f, which we've determined, big F, the vector field, is the gradient of little f. So our answer to the question, is it conservative, would be yes, because the vector field big F is the gradient of little f with the function f that we've just determined. And I want to observe that we've, in a sense, gone above and beyond with this question. We were simply asked, is the vector field conservative? So yes, it is. But note when I say we've gone above and beyond, we've determined a potential function for the vector field. So you may be wondering, is there an easier way to determine if something is conservative before going through this trouble to find the potential? And the reason this is useful is we wouldn't want to go through these computations if the vector field is not conservative. And the following property answers that question for us. It tells us that a vector field with 2 entries, so this is only true for a 2-dimensional vector field, if that vector field satisfies the partials p sub y equals q sub x. That is to say, the partial of the first entry with respect to y equals the partial of the second entry with respect to x. And under some reasonable restrictions that you can read in the book, reasonable in terms of our discussions here in a calculus course, we can conclude that f is a conservative vector field. So if we go back to our question that we've previously been asked, we can actually answer this much more quickly if we're not worried about finding a potential function. So p would be the first entry, y cosine x plus 2. Q is the second component function, sine. And we can quickly compute the partial p sub y is equal to cosine x. The partial q sub x is also equal to cosine x. So py equals q sub x, so that implies for us that f is conservative. And this topic of conservative vector fields will come back up in a few sections when we discuss the fundamental theorem of line integrals. So stay tuned and take care.